Amines are considered weak bases. So strong bases are things like OH minus, OR minus. N with a negative would be a strong base, but N neutral, it's not gonna, it's kind of electronegative, doesn't want to share electrons that much. So because it's a weak base, that means it cannot deprotonate. So instead of acting like a base, it has to settle and act like a nucleophile, a Lewis base instead of a deprotonated base. We have all been there. And the thing, I'm just going off on a tangent, how many did a professor go into like how good a leaving group something is without ever even once talking about how good a nucleophile something is? That was certainly my experience. When I took OChem, not a single professor ever mentioned what a good nucleophile was, but they made me memorize PKs to decide how good a leaving group something was. So I'm going to emphasize that both are important. So once we know that it's a nucleophile, second question, is there a leaving group? Sure. What is a leaving group, Michaela? Great, perfect. Carbon to a large electronegative atom is going to leave very easily. So answer is yes. So if it's a nucleophile with a leaving group, it's substitution. So identifying the reaction is going to help right off the bat. So substitution of the carbonyl, the nucleophile is going to go in, leaving group is going to leave. The mechanism is as follows. So this is going to go in a second. So if you are screenshotting, now's the moment. If not, if you're just going to watch this later and screenshot later, that's fine too. So this lone pair is going to come in and attack the carbonyl, kicks it up here, and you get what's known as the tetrahedral intermediate. Unstable, so this O, once it kicks back in, when this O kicks in, it can either kick out an R group, a Cl, or the nucleophile. What is the best leaving group between R, Cl, and nitrogen? Cl, perfect. So it kicks back in, kicks out the Cl. Eventually, you're going to lose a proton here. It's going to go off with the Cl depending on your solvent. So we're going to end up with an amide. But how many agree? Simple enough. Nucleophile, leaving group, so substitution. Okay, so in this case, again, very small, and it's a weak base. So because it's small and a weak base, nucleophile or base in this reaction, so small and not very basic, so it can't deprotonate. So it has to settle for being a nucleophile. Perfect. Leaving group, Alejandra, you're so far ahead of us. So, or Alexandra, I'm so sorry. But no, it's perfect to be ahead. Are you kidding? This is great. So it's a nucleophile, and you're saying there is or is not a leaving group? Oh, I'm so sorry. It's a name of a friend when I was a kid. So I so apologize because it's just sort of natural. So it's just basically my having bad eyes, not reading well, and just going with the name that most comfortably spoken. So I'm so sorry. Okay, but for this one, leaving group, no leaving group. So it's going to go through addition. It's going to attack, get stuck in sort of limbo because it kicks in, there's nothing to leave. So it can pick up a proton. So for addition, you have to have a second step, and that is neutralization. Acid workup in this case. We had mild acid, protonate, end up adding the C to that carbon, we add an H to that O. Perfect. So we've added across the carbonyl. Okay. Third thing, nucleophile or base. Now we have something with an O minus. So now it's a little bit tougher question. So would OH minus be a nucleophile or a base? Yeah, it's starting to get strong enough to be a base. So OH minus is a base, and this is even bulkier. The bigger it gets, the more or less it's going to be like a nucleophile. Perfect. So the bulkier it gets, the harder it is to get in there. So the more it's going to settle and be a base. So it's going to act like a base. Yeah, see, that's an excellent question. So on the MCAT, they do say you're supposed to know name reactions, but to the best of my knowledge, since 2015, they've shied away from the BS of making you memorize the Bear Villager and the aldol by name, and instead know class reactions. You got to know what a decarboxylation is, what a carboxylation is, dehydration, hydration, hydrolysis, addition, substitution. So these generic reaction names, by all means. But if you're trying to memorize like the Chi-Chi-Bobbin reaction or anything like that, probably not the best use of time. So anybody who took the MCAT, do you remember having to actually identify the Chi-Chi-Bobbin or the Bear Villager? Yeah, I mean, I do a tiny, tiny bit of that in the book, minimal. Yeah, Strecker and Gabriel, because they're specifically named in the MCAT manual. Knowing the Strecker synthesis and Gabriel synthesis methods, yes, you know that. And then you might even know like catecholamine synthesis. You might want to know like barbiturate synthesis. So knowing structures of compounds, but by names, they kind of shied away from that, and I'm grateful. So they made it more like bio. And in bio, are all the enzymes named after who founded them or what they do? Perfect, what they do. I think if you err on the side of that, knowing name reactions based on what they do, you'll be in better shape. Okay, I'm not going to worry about leaving group yet. It doesn't have one, but I'm not going to worry about it for the time being. I'm just going to worry about the base pulling off that H. When the base pulls off that H, electrons can go up. So again, it forms a great nucleophile. Why am I trying the negative on the O and not this structure? Oh, I'll trade questions with you. So why is this one more stable? Why is a negative on O more stable than negative on C? C doesn't like negative charge, exactly. Resonance, always right answer to everything. O is more electronegative, it's going to resonate over. Okay, and the Y does not have a leaving group. Every carbon is bonded to another carbon. So carbon to a carbon here, carbon to a carbon there. Carbon-carbon bonds are too strong, so you can't have them leave. So leaving groups are traditionally O's with a bulky thing attached, O with a resonance withdrawing group attached, or a halogen. But generally speaking, carbon's not a good leaving group. Okay, so what can happen here then? I'm going to get rid of what I just drew and say this can go across. So a couple things can happen. Let's say, for instance, this was an RCl. I'll make it R prime so it looks like something different. What would you get from that? Can you lengthen the chain? Can it go from a short carbonyl to a longer carbonyl? How many remember doing that? Adding at the alpha proton and extending the carbon length? That's definitely one thing I can do. Okay. Could I have it react with itself? So forgive me for this. I'm going to, is it okay if I erase what I just drew here? What if I added it to another one of these same compounds? Can that potentially happen? Actually, let me redraw this in a better way. So can you do that? Can you form a new carbon-carbon bond and make a dimer? And like you said, there's no leaving group, so I could do addition reaction, end up with an alcohol on one side and a carbonyl. So I get an alcohol aldehyde or an alcohol ketone. So an aldol reaction, for instance. So we're going to look at this a little more in depth. But basically, nucleophile leaving group, nucleophile no leaving group, strong base turns this into a nucleophile. And then this is going to react with something that either has a leaving group, like this RCl we did, or no leaving group. So there's really not a lot to this in terms of what it can do. but there are pages and pages and pages of all the different versions of the reactions. And so I'm going to ask you to, as best you can, not get stressed out or information overloaded by some of this stuff. Because how many learned, I'm going to name some reactions, tell me if any of these sound familiar. Aldol, Claisen, Dieckmann, Cannizzaro. Do any of them sound familiar? Two of them. Usually the first two are the ones that sound most familiar. Excuse me. And that's because those are the common ones you learn. But there's such a thing as a Dieckmann and a Cannizzaro, which are basically the same thing as Aldol and Claisen. One has a leaving group, one doesn't. The only thing is they're cyclic instead of linear. Instead of two different molecules reacting, it's one in a molecule reacting with another one. So how many learned of something called the Michael or the Robinson, or any of these names? They're basically an aldol with an extra step, or a Claisen with an extra step where it forms a ring. So they took the same tired reaction and did it over and over and over. Everybody says, I want my name in a book. No, I want my name in a book. Me too. And so they just started basically creating reaction after reaction so that everybody could get their name in a book. You are not the only one bad with names. And fortunately in OChem, everybody throws a name at something. The MCAT does not reward name recognition. That's your OChem professor usually. MCAT, you have to recognize the basic gist of what's happening. Whittle it down to leaving group, no leaving group, strong base turns into nucleophile. Oh, we are. I'm definitely an O-chemist at heart, by the way. And next printing of the book, man, I'm putting my name on friggin' everything. Like, you name it. Every time you turn, my name's going to be there. Dang it! I can't wait, because then I can hang out with my OChem friends. Yeah, I think you did do a ton of these. Yeah, that did pop up one time, that TBR thing, and it's interesting that created quite a lot of friction. And somebody else had said it. So anyway, no, I'm not going to throw my name and everything. Oh, we definitely can. So good nucleophile we covered. You are psychic, Stephanie, because guess what this is? The what is a good leaving group thing. So absolutely, positively perfect. So, and you know what's really cool when this happens? When you are following a lecture and you get curious about what the next thing is, and ends up what you're thinking is exactly what it is, that just means you are so in tune with it. And from a teaching aspect, that's the most satisfying thing around, is when a student is actually totally on the same page. The whole concept of stealing the thunder is awesome. So yeah, let's figure out what makes for a good leaving group. Okay, how good of a leaving group is a halide? I don't know, it's supposedly very good. I memorized it. And I don't know why it is, so I want to come up with some reasoning behind it. Ooh, Brooke, are you trying to get in again?
Sorry, yeah, I'm switching devices.
Okay. Yeah, I felt so bad for you. You're in, but you're not. Okay, so welcome back. One decides something's a good leading group. So I'm going to ask you, as a general rule, if you see somebody's behavior in one situation, do you think it predicts how they're going to be in a different situation? So this is probably more sociology, but would it be reasonable to say that the way somebody treats their pets might be a good predictor of how they're going to treat their kids? So an animal that can't speak but has basic needs to take care of, and you like pick up those nonverbal cues, is that going to be a good call how they're going to be as a parent, early years at least? Yeah. Or, and I mean, I apologize, I'm going off on a parenting thing here, but the way somebody takes care of their car, is that going to predictor in the future of how they're going to take care of things in general? Do they obsess on them? Do they put all these unnecessary accessories on them? Then they're probably going to be wasteful. They're going to wear, like, overdo their jewelry and clothing and waste a lot of money on appearance. Or do they let the car fall apart? Probably going to let their house fall apart. So yeah, oh yeah, how they treat service staff, by so much so. And in fact, okay, again, this is a tangent that I'm going off on that's way too personal, but one of the things I always warn my kids, see how this person treats their mother, because that's going to be a predictor of how respectful they will be of women in general, namely you if you're in a relationship. How they treat their car. Do they waste like money on it? They're going to waste money on other things. Do they let it fall apart? I mean, good predictor. How they treat their pets and how kind they are to waiters and waitresses. And that's, I mean, those are awesome predictors. Okay, how many buy into that? The behavior in one situation will predict another. Okay, that same sociology theory works perfectly in chemistry too. So if I told you that HCl is a strong acid, does that mean Cl leaves or stays with H? Leaves H. So if it's had a habit of leaving from H, can I make an assumption? Well, it's good at leaving from H. It's probably going to be good at leaving from carbon. Does behavior beget behavior? Is this a predictor for how it's going to be in a different situation? Sure. So do you remember O-chemists being kind of over the top about naming the pKa of the conjugate acid leaving group? Did any of you have a professor that made you do that? Give you pKs for the conjugate acid of the leaving group? They do it all the time. There's chapters on it because it's a good predictor. So here's my notion. Because this is such a strong acid, then this is going to be a really good leaving group. If it's good at leaving from H, it's going to be good at leaving from here. So which would be a better leaving group, fluoride or iodide? Why iodide? You're 100% right. Why? So 2 answers for iodide, perfect. It is bigger, perfect. That's a chemical reason for it. Bigger atom, longer bond, weaker bond, easier to break, it's gone. And then also, which is a stronger acid, HF or HI? HI is a stronger acid, which means I leaves from H better than F leaves from H. So I will leave from carbon better than F will leave from carbon. So how many remember, again, doing that, predicting how good a leaving group it is based on how acidic it is when it's protonated? And really, was that sociology that we're doing more than chemistry? Saying behavior predicts behavior, which is kind of cool. Which I don't know, is that sociology or psychology? Not that it matters, but hopefully that seems reasonable. Social psychology, excellent call. Okay, so now let's look at this reaction. I want to make a decision whether this reaction is favorable or unfavorable. Okay, so to do that, I want to look at the 2 leaving groups. Which is more acidic, HCl, or putting H here and making carboxylic acid? Which is a stronger acid, HCl or carboxylic acid? HCl is a strong acid, carboxylic acids are weak acids. So Cl is better at leaving from H than this group is at leaving from H. So is this one also going to be better at leaving from carbon than this one is at leaving from carbon? Meaning my prediction, an acid chloride is going to be a more reactive electrophile than an acid anhydride. In nomenclature, I don't know if you remember this, but why do they call this an acid anhydride? This is foreshadowing. I'm not trying to bias you at all here. But what do you lose when you form an anhydride? And not trying to bias you in any way. And without water, perfect. So if I get rid of water, do I have this compound? Carbonyl with an O, connected to another carbonyl. Okay, so an anhydride then, just basically that compound. So tell me, how can I make an anhydride? Like one way to make it? Could I take 2 carboxylic acids, just heat the heck out of them, drive water away, evaporate water away, leaves that bond? And here's the difference between biochem and ochem. In biochem, do you agree? They say how this happened, you just write the word enzyme and everybody's happy. Enzymes do magic. In ochem, do they always try to say you protonate here, this attacks, this leaves, that forms, and you deprotonate, and ta-da, you get the product? The beauty of the MCAT is it show your work? Do you get any partial credit? Nope. So we're going to take what's known as the biochem approach. Magic. I'm not even going to waste time writing the word enzyme. Just everything is going to occur now by magic. So this is going to be two things. Going to talk about my magic water line and my magic water box. This is a case where I'm making a new bond, so I box the water, get rid of it, and play connect the dots. So this is going to pop up a few times this lecture, but this is the first time. Find the water that's disappearing, find the dehydration water, box it, remove it, play connect the atoms, ta-da, you're a chemist. So this is the magic water box. Eventually, we'll also do something known as the magic water line to predict reactions for hydrolysis and dehydration. But in this case, is this favorable or unfavorable, this reaction? So let me do all the connections I want to do. So let's see. So I'm trying to remember. Acid is a strong acid. That makes it a better leaving group or worse leaving group? So strong acid means it's a better leaving group. Perfect. It's a better leaving group. That means it's more reactive or less reactive. So this one's more reactive. This one would be defined then as less reactive. Which way do reactants go? From more to less or less to more? They go from more reactive, i.e. less stable, to less reactive, i.e. more stable. So less stable to more stable. So this is going to go from unstable to stable. So it's favorable. So we're going from a unstable, more reactive species to a less reactive, more stable species. So how many are okay with that? You can predict the energy diagram by knowing how good the leaving group is. Perfect. And going full circle back to you, Stephanie, do you remember doing this? Is this the kind of thing you were pondering, like predicting how good a leaving group it is, and then deciding how reactive something is? Perfect. Keep doing that. Keep throwing your ideas out, because the more you guys are ahead of the lecture, the more that you're 2 steps ahead of what I'm doing, the better it is. And it's kind of a weird notion. I literally was talking to my wife this morning about this, but how many times have you ever sat in on some sort of talk, a TED talk or something like that, and you get some good ideas from it, but is it more often or not, instead of good ideas, they say something that just reaffirms what you do, and it makes you believe in what you're doing that much more? I mean, how many have ever got that feeling? It's like when somebody else says, yeah, this is what you should do, and you already do it. It's like, yeah, I knew it. Totally knew that was right. And it just reaffirms. Same thing here. If you can be out ahead of the lecture and thinking in advance what it's talking about. Oh, is that what it's called? Is it really called confirmation bias? It sounds like a sociology word. I mean, it seems like something they'd call those sorts of things. Yeah. And me being a naturally sarcastic person, my wife taught me about foot in the door principle. I thought she was totally BSing me. I thought it had to do with like door-to-door sales approach, but no idea it's a real theory. Okay, but for this one, hopefully it seems okay. Downhill we go. Okay, want to click on then. So that's our substitution reaction. How do we decide if something's a good nucleophile? The stronger the base, the more it's going to deprotonate. The weaker the base, the better nucleophile, until it gets so weak that it doesn't attack. So weak bases make good nucleophiles. Strong bases deprotonate alpha protons. Good leaving group, look at the strength of conjugate acid of whatever it is. Okay. Onward we march. This is pretty typical of what you should expect on the MCAT. First and foremost, help me out. What is a barbiturate? Why would that even be on the MCAT? I don't know what that term means, so can you help me? Ah, it's some sort of drug. Perfect. Hallucinant. It's a drug. I'm not even going to try to say the word because I'm audibly challenged. But yeah, so it's definitely some sort of drug. So barbiturate, class of medication. They may have had a passage where they talked about R1, R2, R3, and R4. They may have given you a massive table of R1s, R2s, R3s, and R4s, and some efficacy number compared to when it's all H's. So when R1 is a CH3, or R2 is a CH3, or 3 or 4, or ethyl, and whatever it might be, they might have given you about 9 entries. And again, they might have given you a K of whatever one it is compared to K, like a massive PK table, except this time it was K of reactivity of the one with the R groups versus all H's. And it might have been this massive table, completely overwhelming you. And then they might have asked the question, how do you synthesize it? Is that pretty typical in OChem? Retrosynthetic analysis. Look at a product and figure out where it came from. Happens all the time, okay? So first, let's consider, is this a carbonyl compound? Okay, same set of questions we had. Is it a carbonyl with or without something that came from a leaving group? So I'm going to say this isn't necessarily a good leaving group, but is this something that could potentially leave? Yeah, if we attacked the carbonyl, would it kick that out? So same question we had asked, is there a leaving group or no? That kind of is a leaving group of sorts, meaning it probably went on by substitution or an addition reaction. So we probably form this from substitution or addition. Let's revisit. Let's go back to our very first thing. Addition compared to substitution. So if I add the same thing, let's say we add R and H2, R and H2, good nucleophile, and then leaving group or no leaving group. Has a leaving group. So this is the one that formed the substituted product. This one has no leaving group. So this is the one that underwent addition. Does that sound familiar from just 2 slides ago? Yes, exactly. So everybody read what Stephanie just said? If it is addition, it would be an OH with something attached. If it's substitution, it's still a carbonyl with something attached. So which one is this? Is this a carbonyl with something attached or an alcohol with something attached? It had to be through substitution because it's a carbonyl with something attached. So that means to form this, did I start with a ketone or do I have to start with something with a leaving group? It's a substituted carbonyl, exactly. Had to have a leaving group. Okay, is it okay if I erase this because this base is going to come up computerized in a second here? Okay, so I'm going to erase it in a couple of seconds. 2, 1. So working backwards, I know I break it into 2 reactants right there. So this one had to have a leaving group, nucleophile, nucleophile. So is this then a diketone or a diester that would describe something that has a leaving group? Diester, perfect. Which means, can I get rid of the diketone answers? So diketone would have led to alcohols. These lead to substituted carbonyls. Now it comes down to nomenclature. You agree this is a diamine. It's a carbon with 2 amines attached to it. But how many do not remember the words vicinal or geminal from OChem? You probably said them, you probably heard them, you probably tuned them out right about finals time. Okay, so when this happens, you have to scratch and claw and come up with something. Exactly what somebody just said in chat. Vecino, if you happen to speak a Latin-based language such as Spanish, how do you say neighbor? Vecino. Vecino for neighbor or vicinity. Same Latin root. Perfect. And then how do you say twins? Gemelos and gemelos. Exactly. So gemelos, perfect. So does gemelos, gem, look like geminal? Twins, Gemini. And does vicinal look like vicinity or vecino? Oh, how do I know it's diester? It's not that I knew it was diester. I knew it was not a diketone. A ketone would have an R here, which is no leaving group. So it would have been an addition. This would have been alcohol, not a substitution. So it's that I know it cannot be a diketone. And so it didn't have to necessarily be an ester. That just happened to be my choice. Could have been a dichloro, anhydride, whatever it was, but it could not have been a ketone. Okay, just out of curiosity, for the two people who tossed in like Spanish words, doesn't have to be Spanish, could be French, Italian, any Latin-based language, or just Latin in general. Have you ever done that to survive in a bio class, translated from some Latin-based root? By all means, any means necessary, get things right. Really, in cars, that's never happened in cars. That happened in science. I mean, seriously, being fluent in a Latin-based language helps so much. Yeah, but once you see it, it's like, is it kind of obvious? Wait, were you the one? Oh no, somebody else sent private chat Vicino. Like, yeah, once you see it, it's like, dang, it's easy. I get it. Okay, so hopefully this seems reasonable to you. So is this then, are these twins coming from the same mom, or are they neighbors? These are twins coming from the same mom, so they are Gemini, Geminal, Jimenez. So best answer then C. Let me do one more for you, and I'm going to try to bias you a little bit this time. Believe it or not, I'm going to try to draw things in a hopefully easy to see way. How many remember something in OChem known as a protecting group? Yeah, so vicinal, that's what this one is. Acetals or ketals, exactly. Ah, the Bart Simpson picture, you got it. So you put a little hair on there. And Bart Simpson will protect your ketones. So that, by the way, is stolen from one of the best OChem teachers ever. She taught at UCLA in the 90s and early 2000s. And so she gave the Bart Simpson. She would tell her class, Bart Simpson will protect your ketones. And just a phenomenal teacher. But hopefully that seems okay. So in this one, what was the side product when going from this ketone? And what kind of alcohol was this? It's a diol. Is this a vicinal diol or a geminal diol? Are these two H's on the same carbon, same mom, or are they neighbors? Neighbors, vicinal. So they're vicinal. Perfect. So does that make sense then that you go from here to here? And one step further, what's the side product again? Magic water box. Okay. Yeah, exactly. So again, now I know what the words are. Now if I can, so it is like, so why are we calling this one gem? Because this nitrogen has come from that carbon and this nitrogen. So are they both sprouting from the same mother? Are they twins? So hem, whereas are these on neighboring carbons? One carbon here and one carbon here. This OH on one carbon, this OH on another one. So this, hopefully that seems okay. Yeah, you nailed it. That's exactly what the difference is. Same carbon or neighboring carbons. Okay, so knowing that terminology, how many vaguely remember geminal and vicinal as popping up in your OChem travels? It's weird nomenclature that it's special case nomenclature, but still fair game. Yeah, and if it didn't, so be it. But these are the kind of things that I hope you learn to do. That, yeah, it wasn't covered. And the MCAT, unfortunately, is based on just a different person than you learn from. Now you have to be open-minded enough to recognize things like this. So one, knowing that Gemini means twins and vicinal means neighbor, but then also realizing, are these neighbors or are they twins? Oh, why did I go off on it? So where the heck did this protecting group come from out of the blue? Somebody asked, can you give us an example of a vicinal as opposed to a geminal group? So whereas I did diamine, I went to the vicinal one. So yeah, it was to answer a side question. So yeah, this has zero to do with this question here. So it's just picking up a side note. But perfect. And I mean, and how many, and this is something I hope you always feel welcome to do, to say, wait, what's this about? There's got to be some connectivity. So this was just answering a secondary question. Okay, hopefully seems okay then. Free to move on. And would you put this question in the hard or easy category? This one looks really intimidating and hard at first, and it ends up, if you can draw the line that broke it and decide what it came from, there's your diamine, there's your not ketone. So is this a really hard question with a deceptively easy answer once you're done? Yeah, and that's the most common mistake most people make, is the diketone. So if you look at it like a 2-to-1 ratio, when you look at people did diketone and diester. So it's a really easy mistake to walk into, really easy. But also, for anybody who's taking the MCAT, is this the kind of thing they do? Do they give you some, name that functional group or name where that functional group came from? This is one of their typical little easy, lazy questions that they throw in there. And so it's critical to recognize, is it a carbonyl with something, or is it a carbonyl with just carbons, like a ketone? Easy, lazy. You got test writers are, at the end of the day, are lazy, or they lack creativity. And so retrosynthetic analysis, definitely fair game. And so I want to kill multiple birds with one stone, recognizing leaving group and no leaving group, and then vicinal and geminal from the same carbon or different carbons. Okay, onward we march. Ketal formation popped up. So I'm an O chemist today, so I'm going to use the term ketal and acetal. If you're a biochemist, they're all the same. So for whatever reason, biochemists consider aldehyde and ketone, carbonyl, no matter what, they call them acetals or hemiacetals. But as an O chemist, I'm going to be very anal that a ketal is associated with a ketone and acetal is associated with an aldehyde. So if I had started with an aldehyde here and here, then this would have been an aldehyde, and this would have been an acetal. So just want to make note of that, that's the difference to an O chemist. Ketones make ketals, acetals come from aldehydes. Okay, the mechanism. Again, quick question. How many of you had to know a mechanism or two or a million when you took OChem? Was it 1, 2, or a million? Not a million, give or take. Did anybody notice they all start to look the same after a while? Just like, I don't know about you, but all pathways in biochem start to blur for me. All mechanisms in OChem start to blur. Does anybody suffer from that same plight? They all look the same. I want to tell you that's good news if that's the case. That means you're seeing the commonality in the fact that it basically does the same thing over and over. So I'm going to tell you a couple of things. The key thing here is catalytic H. So what do we know about a catalyst? A catalyst, I think, gets consumed, doesn't it? It's completely consumed in the reaction, or no? It's a TGL moment as always. So what happens to a catalyst? Goes on in the first step and gets released in the last step. Is it regenerated in the end? How many have ever heard that? Catalysts are regenerated in the end, enzymes are regenerated in the end. So the first step I'm going to tell you is protonate. The last step is deprotonate. Put it on in the first step, remove it in the last step, regenerate it. Okay, so if I protonate something, do I make it a better nucleophile or make it a better leaving group? Much better leaving group. Perfect. So if I protonate something, the second step is probably going to be a leaving group leaving. So here's going to be our steps. I'm going to get out ahead of the curve on this one and tell you that the steps we're dealing with are as follows. Okay, sorry if I... there we go. It's finally doing this thing. Okay, so first step, protonate. When you protonate something, you make a better leaving group. So the next step is going to be breaking a bond. Once a bond is broken and a leaving group is left, a nucleophile is free to come in, like an SN1. And then once it comes in, the last step is always regenerate the catalyst. So sequentially, protonate, break, make, deprotonate. Predictable steps. So let's see what we're going to do. We're going to protonate first. Which is a better spot to protonate? An O minus through resonance that's resonance O minus and has resonance because resonance is here, resonate wise, for these OHs. Again, I don't mean to bias you, but the resonating resonance spot with resonance that's resonated were these. It actually was the one I've emphasized. Actually, I'm sorry if I biased you on that one, but how many agree that delta minus, because of the carbonyl resonance, makes this more basic? So protonate on the carbonyl. Now that I've protonated, next step is to break a bond. What is the weakest bond? Sigma, 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 or pi. Again, I'm not trying to bias you, but sigma, 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 or pi. The weakest bond? The pi bond, double bond. So it's going to break. That's actually nothing more than the resonance structure because only electrons move, no nuclei. So I'm going to draw a double-headed arrow. After break, what's the next step? I protonated, make a better leaving group. It broke a bond, leaving group left. In this case, the pi bond broke. Make. Which is a better nucleophile, the left OH or right OH? They're the same, exactly. Don't know which one it's going to be, so it's completely arbitrary. I'm going to choose, apparently, this one. Could have been either one, but it attacks. How many steps to go? I protonated, I broke a bond, I made a new bond. What's the last step? Get your catalyst back, deprotonate. Take that off. And do you agree? I have my final product. This is exactly the same thing as that one up there, yes or no? Dang it. So I have an OR as I wanted, but I have an OH. So it's still two bonds of O, OH and OR, but am I all the way there or am I only one of the two I need? I need two OR groups and I only have one. So I'm all the way there or halfway there? Dang it, only halfway. So do I have an acetal or a ketal or a hemi-acetal, hemi-ketal? It still has an H, so the word needs to be an H. It's only hemi. So if these four steps, protonate, break, make, deprotonate, got me halfway, what do you think I need to do? Another four steps. Do the dang thing over again. So what are the steps again? First step, protonate something. Second step, break a bond, leaving group leaves. Third step, make a bond. Fourth step, deprotonate. So another round of protonate, break, make, deprotonate. So I'm going to protonate this water because I know it's gone in the end. So I'm going to protonate there. Is water a good leaving group? Sure. So it's going to leave. Protonate, break. What's the next step after that? Make. Is it easier for this water molecule or this diol, excuse me, the vicinal diol, to come and go through the solution and eventually end up attacking there? Or is it easier just to have this loop around on itself? So which is faster, intra or inter? Intra, always faster than inter. Inter between two different molecules, going to take forever. Intra within the same one. Okay, which, let me ask you this. If you have an itch that you can reach physically, is it faster for you to itch it yourself or to ask somebody from across the room to run through the crowd and get you to itch it for you? Oh, Yeah, so there's that super lazy factor, but ignoring that, easier just to scratch yourself. Easier if possible. If you're not flexible enough, or it's a spot, how many have that one spot on your back you can't reach? Your 3-member ring, your ring strain one where your elbow is going to break trying to scratch it. But outside of that, if you can reach it, intramolecular is always faster than intermolecular. And then what's the last step? What's the one I haven't taken care of yet? Regenerate the catalyst, deprotonate. Have that come back off, ta-da. Is this mechanism really straightforward? I mean, is this actually a reasonable, fair mechanism? Guess what the steps are if I want to do esterification? Yeah, so you bring up a good point. It's a vicinal diol because they're in vicinity, but in the end, you're getting geminal diether, if you will, because they're coming off the same one. But it's vicinal diol that we added. But you're absolutely right. Vicinal with respect to these two carbons, geminal with respect to that. So, and if you're playing the nomenclature game, by all means. But if I told you pretty much every acid catalyzed carbonyl reaction was the same set of things, protonate, break, make, deprotonate, protonate, break, make, deprotonate, would you believe me that they all kind of follow this with an occasional weird rearrangement? But it ends up, this is actually pretty powerful. This method is lazy and good. So how many are buying into this? How many can see the utility in this? Hopefully it seems reasonable and good. Okay, I'm gonna move on then. Give you about 30 seconds to a minute. Nice work. Why are you not picking A or B? Acetal comes from aldehydes. This is a ketone. Perfect, exactly. Not an aldehyde. So I can get rid of A and B because I have that. Again, I really want to emphasize I'm an O chemist today. When I talk about sugars, they don't make any difference between aldehydes and ketones. And after all, what are most sugars anyway? Are they aldoses or ketoses? For almost all the sugars we deal with? They're aldoses, aldehydes, so it's acetal linkage. So they don't bother distinguishing in biochem. And that's fine. We're good with that. But now, which one is protected? Which one has two ethers, and we know ethers are inert? This one has an ether and an alcohol. Can an alcohol actually react? Can you deprotonate there, kicks in and kicks that out? So hemi is protected, or is hemi still somewhat reactive? This is still somewhat reactive, whereas the ketal and the acetal are those inert. Okay, so both a chemistry question, this is going to become a bio question in a second. Base can react with hemiacetals, hemiketals, but it won't react with a ketal. But can acid react with both? Can I protonate this and make it leave? Can I protonate this and make it leave? Meaning this is protected against basic conditions. This is protected against basic conditions. So like a nucleophile won't react with it, a basic compound, but can acid still destroy it? So it's stable under base conditions, but can acid still break it down? Yes. So let me ask you a different question. If you were going to design a anatomy physiology item, let's just call it a human being, would you want gastric fluids to be basic or acidic? Would you want lysosomes to be basic or acidic? where aqueous conditions start breaking things down. Lysosomes acidic, gastric fluids acidic. So if we have macromolecules that have acetal or ketal linkages, such as polysaccharides, then would you agree we probably would want to have acidic conditions in the stomach? So is that true? Are gastric fluids naturally acidic? I don't know because I don't speak bio, but luckily you're here to teach me everything. Yep, acidic conditions break things down. So that's part of the reason why I think basic is not as useful as acidic as far as, I guess, physiological conditions. Hopefully this seems reasonable. So I want to take advantage of this real quick. We're revisiting sugars just a little bit here. So ketals and acetals are stable in their basic conditions. So therefore, protected and protected. Make note of that. Protected. Protected. Unprotected. Unprotected. So best answer, ketal. Okay. Let me mess with you a little bit. Clicking in 3, 2, 1. The magic water line. So I decided to use something from the book, and I never did this in 20-something years of teaching. Just a couple of sessions ago, I decided, what the heck, might as well take advantage of it. So here's what I want to take advantage of. Notice that we're using acidic water, and acidic water. To the best of your knowledge, let's go back to that gastric fluids and lysosome case. Does acidic water build things up or break things down? Breaks down. So what reaction is occurring when I add acidic water then? Hydrolysis. Exactly. Perfect. Exactly what I'm fishing for. So there is one bond here. So I'm going to do what's known as the magic water line. So the magic water line is draw a line through the bond from the carbon to the leaving group. So that's my leaving group on this molecule. And then water is an H and an OH. There's already an O here. So this side just gets the H, the other side gets the OH. So an OH to the carbon side, H to this side. So you end up with an acid. That OH is this one, and you end up with that. Do they ever make you label where the O ends up, or the H ends up? Has that ever been something biochemists made you do, O-chemists made you do, MCAT test writers will make you do? By all means. So if you can identify that notion, the O is going to go to the carbon because there already is an O on the other side, you're going to be able to predict which way you're going to find it. That question, where does the O go, has been asked, I would say, maybe 2-3 times per year on MCATs. It's nice and easy. Okay, so I want to do another one. So let's see. Nope, not acid water, not acid water, not acid water. Here we go, acid water again. So is this a hydrolysis? So where do I draw my line? Between across the carbonyl, across the bond to R, or across the bond to the N? To the N, perfect. There's my magic water line. H goes to where the leaving group is, O goes to carbon. So you end up with a carboxylic acid, check. And you end up with an H. One of these H's is from there. So here's where it's going to scale up and get a little bit trickier. So let's say I had this compound for my magic water line. Now I have 2 bonds that are broken. Water is going to break a little bit differently. So when it's a single case, OH and H, technically be an OH and H, OH and H, but you're going to dehydrate. So it's easier to say when it's 2, you get an O on the carbon side, and then 2 H's end up over here. So I would end up with RCO, R, so carbonyl, plus an amine. Okay, hopefully seems okay. And now for 3. 3 is simply like a 2 plus a 1. So I'm going to draw my line there. I'm going to hydrolyze that. Acidic water hydrolyzes. So note that I get an O and two H's for two of the bonds, and then an OH and an H for the other one. So on this side I end up with an O and an OH, and this side I end up with a bunch of H's. How many can be lazy? How many can see the utility in this lazy approach? Perfect. Hopefully this seems useful and good. That said, are there ever any hydrolysis reactions in biochem mechanisms? Sure. So learning the magic water line, hydrolysis ATP, exactly. So if you do it that way, we now have phosphorus instead of carbon. But let's say I want to break the linkage like that. Oops, sorry, that was meant to be a P. Something like that. Same thing, magic water line. If I drew the magic water line there, O gets an H, this gets an OH. Is it the same thing? Draw your line, put your water in, ta-da, you have your products. Magic water box, magic water line. Okay, so moving into applying this, I'm going to click in 3, 2, 1. Moving to protecting group. So there's my protected, my ketal or acetal. I can't tell which one this is again. Ketal, perfect. So acidic water, for acidic water, am I going to draw the magic water line or magic water box in this case? Hydrolysis or dehydration? Magic water line. So my magic water line is going to go right there. And what do I put on which side? What does carbon get? Does carbon get the H's or the O's? Carbon's going to get your O, the other side's going to get your H's. So let me get rid of my terrible writing. You end up with that compound. Beautiful. If I use mild acid, that works out well. I also protonate there, just point of interest. But if I use an acid that's too strong, is that ever a problem? One of the mottos in OChem, aim high or aim low. Overdo it or barely get it done. Sorry, excuse me. Barely get it done, aim low, barely get by. Get that A minus when really what does an A plus or A really do for you? Aim low. So in this case, if I use too strong of an acid, is it possible I can protonate a second time here, make water, it leaves and get elimination? So if you use too strong a reagent, you get side products. So mild, barely get it done, we get what we want. Too strong, doesn't work out. And then no acid at all, it's not going to do anything to it, can't hydrolyze without a catalyst, no reaction. So our goal in OChem, use the weakest possible reagent we can to get it done, don't overdo it, and don't underdo it. So does this seem okay? I mean, does this sound somewhat familiar or seem reasonable? Perfect. Moving on then. So magic water line, magic water box. We've done the magic water line. So let's see how you do for this one. Good question. How do you know whether it's a box or a line? Well, how do you know whether you're adding water or removing water? What could you tell? If water is on the reactant side, then it's hydrolysis, you're breaking a bond, magic water line. If water is on the product side, you removed it, dehydration, magic water box. So line on the left, box on the right. So it all depends on where your water's ending up. In exchange, what is a glycosidic linkage? Oh, you're very welcome. Glycosidic implies it's a linkage between two sugars. Perfect. So tell me, what sugar have I drawn here? I don't recognize this one. And this might be verbatim of something from a WMC item of some sort. The quickest and easiest way is to decide, is this straight chain, Hayworth, or chair representation? These are chair conformations. For chair, the easiest way to find these things out is decide, are we looking at axial or equatorial substituents to make something really stable? Which is more stable, equatorial or axial? Equatorial. Going one step further, is cellulose the most stable starch we know? Is that the one that plants build their structure out of because it's so stable? Is that the one we don't really break down? So tell me about cellulose. Is cellulose filled with a bunch of axials or all equatorial? Everything's equatorial. Beta-D-glucopyranose, everything's equatorial. So that's a glucose. Does this one also have everything equatorial, or is there one random axial? There's one axial at carbon 1, 2, 3, 4. Same professor, her mnemonic she told her class that I absolutely love. She said in her perfect world, she believed there should be 2 men for every gal. What the heck did this mean besides she was living a life of decadence? So what was her mnemonic telling her class? 2 man meant what? If it's C2 that's axial, it's mannose. If it's C4 that's axial, it is galactose. Perfect. So this is a beta 1,4 linkage between galactose, because it has number 4 axial, and glucose. So what sugar is this? What disaccharide specifically? What has galactose 1,4 beta linked to a glucose residue? And I gotta admit, some will be okay with this one. Some of you might be intolerant to this particular one. This question. Iman nailed it. Lactose. Should you know your common monosaccharides and disaccharides? Yes and yes. So would you say lactose common or rare? Common. Fructose connected to glucose in a alpha 1 beta 2 linkage is sucrose. Should know that one. Beyond that, we'll worry about them as we come to them. But for this one, galactose to the glucose. So I'm going to get rid of everything I have here. So erasing in 3, 2, 1, gone. Fructose and glucose make sucrose. Exactly. Yes. And specifically, it's between 2 anomeric carbons. So it's bizarre. And we'll get into that when we do the sugar lecture in a little more detail. But yes, sucrose is a weird one. Even though it's so common, it's just a weird linkage. It's a 1,2 linkage, which is rare, between 2 anomeric carbons. Okay, so for this one, you're going to break the glycosidic linkage. How do I find anomeric carbons? How many bonds to carbon in the anomeric carbon? The one that used to be the carbonyl? Or how many bonds to O, I should say. Yeah, every carbon has 4. I apologize for that. What I meant was how many bonds to O in an anomeric carbon? So the carbonyl has carbon with 2 bonds to O. It retains 2 bonds to O. So this carbon right here, is that anomeric because it has 1, 2 bonds to O? And is this one also anomeric because it has 1, 2 bonds to O? So I'm going to refer to this as an acetal linkage because it came from an aldehyde because there's an H there. But is this one acetal or hemiacetal on this side? This is only hemi. So let me ask you this, kind of a weird question, but they love to ask this. Is this a reducing sugar? Why? Why is it a reducing sugar? The answer is yes, you're absolutely right. Why? It can be further oxidized. This comes from an aldehyde, and I know aldehydes can get oxidized. And this is protected or unprotected? Unprotected. This is a reactive aldehyde. Aldehydes can oxidize. It's unprotected, so it can react, which means it can get oxidized, so it can act like a reducing agent. It is reducing sugar. One of the dumbest questions they ever ask in biochem, but do they ask it a lot? Yep. Okay, so now back to what we're doing. Hydrolysis of the glycosidic linkage right here. I'm going to break the bond from the anomeric carbon to the leaving sugar. OH goes to the carbon, H goes there. So let me erase everything. 3, 2, 1, gone. And my equipment is just behind. So there we go. So does this seem okay? You did not oxidize an aldehyde. You did not deal with an ester. You dealt with an aldehyde and an aldehyde. Okay. Were you protecting or deprotecting when you broke a bond? Deprotecting. Perfect. So water is a reactant, not a product. Hopefully it seems okay. You're going to be going hydrolysis, magic water line, as opposed to a magic water box. Okay, onward we march. So just in curiosity, what made it tough? So what were the things that were tough on this one? Because if you, sorry, if you can break it down, that's the best way to correct yourself. And how many realize that usually how about now? Oh, wow. Technology. Hey, what do you mean welcome back? I never left. You guys left. It was you. So anyway, sorry about that. I have no idea. I think just the plug and unplug thing. Okay. So basically the question was asking for this one, what makes it tough? Lots to know. I think, yes, they're actually really good about writing the sugar. Yeah, and I left it blank for that reason. So I'm maybe a little bit unfair in that sense, is that I write questions with less information they give. What they might do is give you 3 different disaccharides in the passage. So they might write it 3 different ways. And whether it was lactose or some other sugar, just recognizing that you're going from 1 dimer to 2 individual monosaccharides, you have to add water across it and then which way it goes. But for those who take NAMCAT, would you agree they give you more than you need? Yeah, exactly. You parse it out with time. And honestly, one of the things that I seriously think you guys need to get used to is to recognize what matters and what doesn't matter. And again, people who take NAMCAT will confirm they usually give you more than you need as opposed to less you need. They generally overdo your information. Okay, onward we march. The aldol condensation mechanism. Okay, did you, oh, yeah, acetal and ketal simply is ketal came from ketone, acetal came from aldehyde. The first example I showed a ketone reacting, so we were doing ketes. This last one, sugars, they were both aldoses, they came from aldehydes, so I referred to them as acetals. But did you notice they didn't even look any different? It's still the same thing, a carbon with 2 bonds to O, 2 ethers. Just matter what the original compound is. It's a nomenclature thing. So it's almost, I need to bring it up because it is a word, but it's also too much. It's like a minute detail that I'm overstressing. Okay, again, we deprotonate. This can resonate over, as you mentioned. Is it possible to protonate on this? So an H came off here. Is it possible to protonate there? So how many learned this term where you get a ketone, deprotonate it, resonates over, and you protonate somewhere else, and instead of a ketone, you now have an enol. En for double bond, OH for alcohol. So does that sound familiar? The ketone enol? They're a special case of isomers known as tautomers. They vary by where you protonate. So the H in a pi bond vary. Deprotonate, resonate, and reprotonate somewhere else. Okay. This is fairly common. This is keto enol tautomerization. Could also have aldehyde enol, but yeah, ketone enol, as I've drawn it, exactly. So bio has an example. You tell me where the heck this comes from. So from the enzyme, should that give me any hint at what's going on? So from this, I know it's an enzyme because of ACE. What is enol? Double bond with an OH. So do I, in the product or reactant, pointing the wrong way, but the reactant of the product, do I have a double bond between carbon and carbon? Product, perfect. On that double bond, do I have an O that instead of being an OH is a phosphorylated OH? Hence the name, phosphoenol. So would that ever happen? I have no idea if you would actually have a weird reaction like that, phosphates coming on and going off and pyruvate being formed. That'd be weird, or would it? Where does this show up? Perfect, glycolysis, exactly. I don't think it's in the TCA cycle. I think pyruvate gets consumed. Maybe it is. And honestly, I don't know. I just know this is one of the last steps of glycolysis. Do not get caught up in the minutia. Know what happens. So in glycolysis, what do you start with and what do you go to? What do you go from and go to? Glucose, perfect, 6 carbons, into pyruvate, which is more than 6 or less than 6, I can't remember. 3 carbons. So is that a buildup or a breakdown? That is a breakdown. So what causes things to break down? Rusting away or building up? Adding a bunch of things together to make a longer chain, or rusting away and breaking into smaller pieces? So generally speaking, breaking down processes are oxidative, typically speaking. Building up processes are reductive. And again, thank you, Major League Baseball. But what do we know about the steroids taken by our admired baseball players? Anabolic or catabolic steroids? And how many actually remember it that way? How many remember baseball is filled with anabolic steroid users to make themselves bigger or smaller? Anabolic, Jason Giambi, perfect. Ken Seiko, perfect, definitely. People got abnormally large. Reduction, build things up. Anabolic processes are buildup. We make macromolecules. Therefore, catabolic processes do what then? oxidative and break things down. Oxidation typically gives off energy, so catabolism typically releases ATP, NADH, and other energy molecules, whereas anabolism stores or consumes your energy. Don't want to go catabolic, bro? Yeah, if that works, whatever way works. I actually remember, thanks to Major League Baseball, anabolic steroids builds everybody up, reductive buildup, energy storing. Yep, energy storing, endothermic, exactly. Perfect. Generally speaking, there's obviously going to be a few exceptions to the rule, but yes, you invest energy to build things up, to store it, to break it down later. So is that what we build up fats, for instance? We're building up fats for lubrication or for energy storage in most cases. I should be careful because cell wall or cell membrane also involves it, but generally energy storage. So endothermic processes, we store energy. We pump energy into built up molecules. We get it when we break them down. Okay, glycolysis step, hopefully seems okay. Get rid of my circle. And the aldol reaction. Because OH is about 1/100th as reactive as this H, now only a few get deprotonated. So I get 1 deprotonated for every 100 of these. So attacks, I go from 1, 2, 3 carbons to 1, 2, 3, 4, 5, 6 carbons. This was an addition reaction, no leaving group. So I end up with this, which I can do deprotonation, but how many have ever heard of beta hydroxyketone? I'm a ketone and 1 2 carbons weight beta. So instead of saying 1, 2, 3, 4, 5 and counting up the chain length, instead we simply say away from the carbonyl, 1 away is alpha, 2 away is beta, 3 away is gamma. So does the term beta hydroxyketone sound at all vaguely familiar to you? Okay, perfect. It's a really common product from these sorts of aldol condensation reactions. Okay, again, knowing bio is key, knowing shortcuts. So do you think this is going to be hydrolysis or dehydration that gets me where I want? Am I breaking one thing into 2 pieces or taking 2 things and combining into 1? So the aldol go from a 3 plus 3 to make 6, or is it 6 breaking into 3 plus 3? Dehydration this time. We're now forming new bonds and getting rid of water. So the magic water box or magic water line, if I'm forming, perfect, magic water box. My magic water box, get rid of my water. Ta-da. Easy as lazy. So I'm going to take this one step further. Everything I did so far has been symmetric. 2 ethyl groups here, the previous one had 2 methyls. But if I have a methyl one side, ethyl on the other, ethyl here, methyl, which is going to be harder to reach? The crowded ethyl side or the less crowded methyl side? Less crowded and easier to form, but which is going to be more stable? A double bond with 4 R groups or a double bond with just 1, 2, 3 R groups and an H? So I'm going to learn the more things you have, the more stable. 4 R groups. So this is going to lead to a more stable compound, but this is going to lead to the easier to form transition state, the faster compound. So quick thermo review. Where do I worry about faster? Where does faster happen? How many learned that? Kinetic is the faster one. Thermo is the more stable one. Does that sound familiar from your travels? Okay, so let's say they gave this really bizarre passage where they're saying we're building artificial cell membranes. We're simulating it by forming these, it's basically a whole bunch of lipids that aggregate into a micelle. And you get one that forms right away, but if you agitate it and leave it for about an hour, it turns into a different one. Was the first one your kinetic or thermodynamic analog. Kinetic. The one that formed after a lot of time was your thermodynamic one. Perfect. Okay. Those are the kind of terms you have to be able to apply. So kinetic forms easily, thermo more stable. So let me get rid of what I've written. 3, 2, 1, gone. And for this one, here's my magic water box. The magic water box here. How many are okay with the magic water box and the magic water line? Lazy is good. Figure out what you have. It is the biochem laziness applied to OChem. Okay, always have to do bioexamples, just sort of obsessed with them. What molecule is this that I've drawn? If I told you this was possibly something to do with plants, but more importantly, if I told you this came from glucose, would you believe me? I told you that's glucose, yes or no? Glycerate's not quite right. You're close, but not quite yet. It is 1,6-bisphospho, but is it aldose or a ketose? It is a ketose, whereas glucose, mannose, galactose are ketoses or aldoses. Those are aldoses. So this is a ketose. This is actually fructose. So this is 1,6-bisphosphofructose. Does that sound vaguely familiar? We're talking glycolysis again. Yep. And when you see it in that sort of context, see it with everything else. But is there a step where you go from a 6-carbon fructose and somehow, some way, magic, you break a bond between carbon 3 and carbon 4? You end up with a 3-carbon fragment and 3-carbon fragment. Does it really happen? Does the 6-carbon glucose break into 2 3-carbon fragments? You bet. So is this building up or breaking down? So it's part of an overall oxidative process, which glycolysis is. You go from 7 bonds O to 10. So you definitely have oxidized and you definitely broken down. But more importantly, is this an aldol or reverse aldol reaction? Reverse aldol. You're going from a beta hydroxy ketone. Here's my ketone, 1, 2 ways of beta. That one's going to kick in. But the beautiful thing about enzyme nomenclature is enzyme named for what goes forward, what goes backwards, or either one. The same enzyme goes either way. Same catalyst either way. So what enzyme do you think is responsible for carrying out this reverse aldol reaction? Not that I'm trying to bias you, but what enzyme? Aldolase. Perfect. So named for the OChem reaction. One of the rare cases, aldol reactions, because the original one they studied was an aldehyde alcohol, named after what you get, not the person. There is no Dr. Aldol. So hopefully it seems okay. So far, so good. So thermokinetic, slip that one in, magic water box, important bioexamples. So notice everything has a bioexample, because what do they love to do on the MCAT? Ask you straight OChem questions or OChem questions about bio-related molecules. For those of you who've taken the MCAT, all bio all the time. Yeah, let me go back to the magic water box. So this one right here. Let me escape back. It's taking a second. I apologize. There we go. So the magic water box, find the H's you're losing. Both of the alpha protons here get lost, and the O of one of the carbonyls. So I'm adding 2 molecules together, and all I gotta do is identify the water, write my box, get rid of the water. This carbon needs 2 bonds. This Carbon needs 2 bonds, so they find love and happiness with each other. So you end up getting that bond connected there. For this one, 2 alpha hydrogens on one, the O on the other. Get rid of that. Double bond there. 2 H's on that, O here. Magic water box. So does that seem okay? It's the trick is identifying it. Yeah, basically, I just call it a box and a line just to memorize it. There's nothing sacred about it. Just I'm engulfing or surrounding the water that I lose. So if I box the water, remove the water, and add across. So it's me just being cutesy more than anything. So magic water line, we break it, add water across. Magic water box it the water, get rid of some water. So hopefully this seems okay. Oh, you're very welcome. Then there's our bio example again. And onward we march. Swear, gonna march any second. Perfect. You have 20 seconds to get this one right. And the answer is beautiful. Why did you say, I mean, for the answers that popped up, why are you not going with A or B? Because glycolysis builds things up or breaks things down. It's a breakdown. Perfect. So I know it's reverse aldol. Aldol makes a longer chain. Reverse aldol gets rid of it. I forget, what do you get from glycolysis? This is rote memorization. Glycolysis turns into what? Glycolysis turns into a couple pyruvates. Perfect. So you get 2 products, not 3. So only 2, and they are 3 carbon species, which eventually you end up getting pyruvates from these. How many learned DHAP, dihydroxyacetone phosphate, along with glyceraldehyde 3-phosphate? Yep. And I'm gonna actually argue against that. So I got somebody to respond to a private message to say, I don't know if this is tricky as much as this is half tricky. Half is straightforward, I know we're breaking down, but then remembering where it applies. So this is both has a simple portion and a tricky portion. And those are always where it's easy to get slipped up. But just process your information as best you can. Okay. The last part of carbonyl chemistry to make it complete, redox chemistry. And I've already forgotten. Luckily, you're here to help me out. What is reduction to an O chemist? Reduction is gain of O's, isn't it? Reduction is gain of H's. So hydrogenation, reductive process. So what is oxidation then? Gain of O's, perfect. So reduction, gain of H, oxidation, gain of O's. That would mean loss of H is oxidation, also bonds to O. So oxidative or reductive? Perfect. Oxidative or reductive? Oxidative, perfect. Because I've inserted an O. Perfect. Hopefully these things are nice and straightforward for you. Okay. Reminder, when you gain bonds or gain electrons, gain bonds to more electronegative atoms or gain electrons, oxidation state goes down. When you gain bonds to more electronegative atoms or lose electrons, oxidation state goes up. Oxidizing agents, you're named for what you cause or what happens to you. Even though I totally ruined it by clicking too far in advance. You're named for what you cause. Oxidizing agents cause oxidation, therefore they themselves get reduced. Again, this is such an annoying term, but we got to know it. So oxidizing agents get reduced, reducing agents get oxidized. I will once again confess, like I do every time, I have to say the same thing over and over and over. I have to keep on saying oxidizing agents get reduced, reducing agents get oxidized. It's one of those brain fart moments that I'm totally accepting that's who I am. That's how it works. I want to do the, if it looks alike, it reacts alike thing. What does NABH4 react with? Can't remember. Those who've taken OChem. It's one of the weaker hydrides. It only reacts with aldehydes and ketones. So what does NADH react with? I mean, how many agree? Those look an awful lot alike. They both begin with N, have H. They both have a consonant that nobody ever picks in Wheel of Fortune. They both have an A. I mean, the 4 there, but if you just ignore the 4, if I cover it up, they look really close. They end up doing very similar things. So for carbonyl reactions, we typically use NADH, possibly NADPH, depending on where it's occurring. And then how many remember PD or any metal with H2 adding H's across a double bond? Does that sound familiar? So PD in H2 or FA in D. So P, D, FA, D, H2, same thing. So this deals with alkene reactions, carbon-carbon double bonds. This deals with carbonyls. Good general rule, when in doubt and you're looking at a pathway, that'll work. NADPH deals with everything, unfortunately. It doesn't really follow its own set of rules, so that's why I haven't included it. But rich in H, reducing agents, rich in O, oxidizing agent. Would they ever give you a reaction and ask you what is it coupled with? So if I said I had a C26 carbonyl compound going to a C22 and C4 compounds, I'm going to tell you I would couple this with FAD going to FADH2. Yes or no? No, because it's a carbonyl. So mess that one up. No problem. I'm going to go from NAD plus to NADH. Yes or no? So NAD is correct for carbonyl, but now the question is this oxidation or reduction when I go from 26 to 2 fragments? When it went from one thing to 2 things, was that oxidative or reductive? Was that a buildup or a breakdown? I go from a chain of 26 carbons and I break it into 2 fragments, that's oxidation. So that means the other reaction must be reduction, the one that I couple with. Is this reduction, is NAD plus going to NADH reduction or oxidation? Yes. So the statement is breakdown oxidation? Yes. Just like anabolic processes are reductive and they build things up, so we reductively make macromolecules bigger, we oxidatively break things down and eventually turn them into CO2. So hopefully it seems okay. So reduction to couple this oxidation. So is that true? Does oxidation always balance out reduction? Do they go as a pair? Is it redox or red-red? Redox. So for every red, I must have an ox. So if the carbon species is the ox, then the coenzyme has to be the red. Okay, hopefully seems okay. It's going to toss a couple reactions at you. 3, 2, 1. Selective oxidation, meaning I want you to tell me what you think is going on in this case. Is this an oxidizing or reducing agent? Rich in O, it's an oxidizing agent. So I'm going to go from protected, who cares, an aldehyde or alcohol. What is this compound? Primary alcohol, perfect. This primary alcohol has two H's to lose. It's going to lose them one at a time. If I lose one H, get one less bond to H and one more bond to O, go from primary alcohol to an aldehyde, it goes there. How many learned this is PCC and learned that this stops it at the aldehyde rather than going all the way to the carboxylic acid? Does that sound familiar? The PCC, pyridine with CO3 stops it? If it doesn't, that's fine. But selective oxidation, meaning I'm going only one H at a time. I have two H's to lose, it only loses one of them, not both of them. Okay, oxidation state, just real quickly, a couple different ways to get oxidation state. For OChem, the easiest way is look at each of the bonds the carbon makes. So carbon and carbon are equal electronegative, so we give them both zeros. Carbon and hydrogen, carbon gets a negative, H gets a positive, because carbon is more electronegative. C and H, negative on carbon, positive on H. O is more electronegative, so negative on O, positive on carbon. So carbon's oxidation state, I add up everything in its sphere of influence, 0, negative, plus, and negative. Two negatives and positive means overall -1. In the end, bond to carbon is still 0. Now two bonds to H's, so plus and plus, and then bond to H, so negative. So 0, positive, positive, and negative means +1. Has this been oxidized by 2 electrons? Has it gone from -1 to +1, meaning oxidation state changed by 2? Sure. So was it coupled with some other reaction? In this case, this was CO3 was getting reduced. But if I'm doing biochem, oxidized by 2 electrons, if I told you that this went from NADH plus H plus to NAD plus, would you believe me? Are you buying into that? Why not? Gosh, I've messed this up again. What have I done wrong? Got it backwards. Reduction means it had to gain the H. So, nab it. So the reaction we get will be something poor in H, going something rich in H. So it's got to have H gained in the end. I have to go NAD plus NADH plus H plus. So NAD, because it's dealing with the carbonyl, and then this gains H's because that lost H's. How many are okay at recognizing that? How many saw my error right away? Perfect. So this is pure unadulterated memorized OChem. This is biochem. Which one is going to be on your test, OChem or biochem? Both chem. Going to get all of it. So if you start seeing NADH, NAD+, FADH2, and FAD is just nothing more than other OChem reagents, it'll help you understand both OChem and biochem a little bit better. Okay, so clicking in 3, 2, 1. I fat thumbed it and did a little early. Overall review of things. How many H's on a primary alcohol? 2. So how many H's can it lose? 2. Like we mentioned, it could lose 1 and go to the aldehyde, but then there's still 1 here, so can it go all the way to the carboxylic acid? So primary alcohols can be oxidized up 2 levels, 2 H's to lose. Secondary alcohols, on the other hand, only have 1 H to lose. They can only be oxidized up once. And tertiary alcohols do or do not get oxidized very easily. They don't. Grignard can add an R group. I'm going to ignore it for now because it's kind of I mean, whether it's removed or not, they no longer formally say Grignard is fair game, but technically it's still a nucleophile. So it's basically an R with a negative charge that can come in and attack and do addition. So it's a reductive process. I'll just leave it as that, the reduction, because the number of bonds O went from 2 to 1, 2 to 1. Common reagents you need to know. Have to just flat out memorize things. Chromium in +6 oxidation state, lots of O's, oxidizing agent. Manganese in a +7 or lots of oxygen state, oxidizing agent. Reducing agent. Reducing agents, lithium hydride, Al with NH, or sodium borohydride. Have to memorize these. Hate to say it, but there's a certain amount. And then Grignard, up to you if you want to remember this one. This is kind of, if you don't know it, you're probably going to be fine. But these, rich in O, oxidizing agent, rich in H. How many have definitely seen chromate, permanganate, lithium hydride, and sodium borohydride multiple times in your OChem travels? How many agree? Yes, those all 4 look familiar. And yes, I've forgotten them because I don't study it every day. But key thing, recognize it. Also, recognize things in context. Be able to fake your way through stuff. So is this, I think this is in the handout now, isn't it? Except without the cool blue circles. Is it or is it not? I always forget whether I put it in there. I know it wasn't in there and I thought I put it in. It isn't. Okay, thank you. Okay, because I was going to say screenshot, but if it's in the handout, no, not as big a worry. Random other reactions. Tell me what you think this reagent is going to do. Do you believe this is a oxidizing or reducing agent? And tell me the logic behind it. So why is it an oxidizing agent? Nail it, Jonathan. Rich in O. How many are bothered by the fact it says 3 instead of 2? Does that make anybody upset that that's a 3 instead of a 2? Upset's a strong word, but this is called a peroxy acid. You probably learned this as MCPBA, metachloroperoxybenzoic acid. But a peroxy acid, like a peroxide, has more O's than it should. Oxidizing agent, it's going to give one of those O's away. So I'm going to write it in blue because it's oxidative. Known as a bare villager oxidation. If you're collecting names, if you're not collecting names, don't worry about it. But it inserts an O into the ester, into the ketone to make an ester. Okay, what is this compound right here? So let me put the names here. So MCPBA. This one you have to know. It is an ethanol with 2 carbons. On one end, you have the O on the first carbon, second carbon, the beta carbon, you have an S. Sulfur is really good at picking up mercury. If you spill mercury, add sulfur, it'll bind it. This is not DME. Close. Does a very similar thing. Beta something or other. Exactly. This is beta mercapto because it captures mercury. It's one word, but I just ran out of room. So ethanol with a beta sulfur, a beta mercury capturing group, beta mercaptoethanol. So is it rich in H or rich in O? Rich in H, so it's reducing or oxidative? Oxidative. No, I'm just making up words. Reducing agent, perfect. Rich in H. So it's gonna break the disulfide linkage. Your cysteine linkage is gonna go back to 2 cysteine residues. In exchange, this gave an H and this gave an H, so 2 of them, they end up getting the bond. So the SS bond with 2 SHs turns into SS bond with 2 SHs. It's just, they trade partners. Hopefully seems okay. Ketone. This one, I see a lot of H's, I'm good. This one's a little bit weird. The H is normally not a reducing H, but when I had zinc, can zinc provide electrons? So zinc with a source of H's can now provide H minus to add to this. We have plenty of ways to reduce this down to an alcohol, NADH and aluminum borohydride, but this one reduces both bonds. So they're reductive because of the rich in H. Unit with an alkane, you replace the O with two H's. When it's under acidic conditions, with this particular concoction, it's Clemmensen reduction. When it's with this hydrazine molecule, it's Wolff-Kieschner. How many agree this is pure and unadulterated memorization that shouldn't be done as memorization, instead should be done as recognition? Lots of O's, oxidation, and H, reduction. H with electron source, lots of H's, production. Your job on the MCAT is to memorize and know everything, or to recognize things in context, stay calm, cool, and collected, and apply your basics. Which is a better approach? Memorize, know everything, or take what you know and apply it? Know your basics, apply it in context, and honestly, more than anything, and this isn't news to any of you, but how many agree when you stay calm, better things happen? That's the hard part. You nailed it. It's so easy for me as a teacher because I'm not going through the same stress. Like, oh, just relax. It's all going to be okay. Don't worry about it. But how many realize that's BS? You're going to freak out and every now and then on the test. But be fair to yourself. Don't try to go through the test not freaking out. Instead, go through the test recovering. And again, every time you get stressed out, stop for a few seconds, massage your fingers, take a deep breath, and say, thank you, body. Thank you for being fully aware of the circumstances and responding in a natural way to help me perform better by giving me more adrenaline, more energy. So stress is good. Stress is your friend. So when I freak out, I'm going to catch my breath, I'm going to think straight, and I'm going to say, thank you, body. So you got to go from stressing out to being grateful for the extra energy your body's providing. No, but ironically, I used to run a lot and actually did run for that. Are you serious? Wow, maybe it's something that genetically predetermined by our last name, which ironically isn't actually genetically my last name though. Oh, I believe you're serious. That's so interesting. Sorry, I'm having a private conversation with somebody who said there's somebody with the same last name. Used to say that same thing. No, I was actually inspired by hearing a speaker by name Karch Karai. He was an Olympic coach, just coached the women's volleyball team. And I've been fortunate enough to be like a friend of a friend connection and be able to talk to him and hear his perspective on it. And it's just genius. And that's exactly what it is. Channel your energy. Stress is a good thing. Stress is what gets you up. Too much stress and mismanaged stress, bad. But well-managed stress will help you get a better score. Okay, for this one. Thank you for acknowledging it. So is that, okay, real quickly, like mentioned earlier, was that a case of new information or is that reaffirming something you already discovered? Yeah, reaffirming. Anxiety mismanaged, terrible. Anxiety managed the right way is power. It's fuel. It's what makes overachievers achieve. Okay, strongest reducing agent. Can I throw away anything right away? Anything that you say is gone. Lots of O's. So how many agree A is out? A is the worst answer of all. Okay. Now, these all have H's, H, H, and H, but is it hydride or hydronium that I need? Do I need an H minus or H plus to be reductive in nature? I need H minus hydride because this is called lithium hydride, sodium borohydride. This is ammonium, IUM, when I have the H's on it. So H minus is what's actually attacking. So if I drew this out a little more anally, I would draw H minus with a lone pair. And that's how the reduction is occurring. So it's got to be an H minus. Okay, so with that in mind, ammonia is actually acidic. It's going to keep the electrons, not donate them. So that's not going to work. That one's out. So I'm down to two choices. Sodium borohydride and lithium hydride. So what do you think they're both hydrides. They both are called hydrides, so they're H minus. Which one is more electronegative, B or Al? I can't remember, but luckily I know that B is above Al in the periodic table, and you can teach me something as I go up. What's true? More electronegative. So according to this, if Al is less electronegative, is it going to donate H more readily or less readily? So if it's less electronegative, it holds on electrons less tightly. It's going to share it more. So aluminum is willing to share electrons a lot, or on not as much. So is this one going to donate a little bit more? And how many just memorized that when you were in school, that lithium hydride is a strong one, it reduces everything? Sodium borohydride reduces just a little bit. Yeah, and exactly, how many TA that said this stuff catches fire if you spill it? Yeah, there's a lab at UCI where the person, just one of those freak accidents. They were carrying a bottle of aluminum hydride. They were coming in the door, and this is back when phones were connected to the wall. People would use phones. Somebody on the phone was leaning back and turning around and didn't see them. They collided, the wall and caught fire. The phone melted. It was pretty impressive. It was terrible. Nobody got hurt except for the phone, but it just melted everything. It was just, I mean, it was just pretty massive because it is pretty nasty stuff. Best answer though, lithium hydride. You may also just flat out memorize that sodium borohydride only reacts with aldehydes and ketones. Lithium hydride reacts with everything, every last thing you can touch it with. So the more reactive one, lithium hydride. Hopefully this seems okay. There is some memorization in OChem. Hate to admit it, but let me click on one more thing that I want you to know about carbonyls. One last important thing. Oh yeah, that's not the thing. Here's the important thing. Carbonyls, you may not even notice it, but they can give you information, give you directions. They can guide you and tell you what to do. They can tell you it's actually time to head for the exit. They are very informative. I cannot believe I finished right on the dot at 3. So this was actually so well managed time-wise. Yeah, I mean, seriously, I'm on borrowed internet, so I officially just went over the second of good taste. Thank you guys so much. Appreciate it. And again, it's awesome because you guys, it's a give and take. You guys are such a great class for how much you input, how many ideas you share. And I friggin' love that you keep on answering. It seriously is so cool. It's the best thing in the world as a teacher when you have an engaged class that participates. And you guys are pretty damn smart. That's also adding to it. And again, I want you to acknowledge each other. How many definitely recognize you have a lot of smart neighbors, and you are one of those smart people in that group? It is very, very cool. You can see like things starting to click, and there'll be some pretty impressive scores coming out. So anyway, I'm going to sign off just because I'm getting my little warning. I will see you. Yeah, see you on Sunday.